In this video, we will prove three results. One is, if I is a homomorphism, then kernel of that homomorphism is a normal subgroup of the domain. And if phi from G to G bar is an onto homomorphism with kernel K, then the set of all inverse images of an element, say G bar in G bar, under phi in G is given by Kx, where X is any particular inverse image of G bar in G. And if we have isomorphic to be a relation on the collection of all groups, then this isomorphic relation is an equivalence relation on the collection of groups. So first we will establish that if phi from G to G bar is a homomorphism with kernel K phi, then this K phi is normal subgroup of the domain G. So first let phi be a homomorphism of G into G bar with kernel K. To prove that K is a normal subgroup, we have to show that first of all it is a subgroup for which we need to first have that to be non-empty. So kernel phi is non-empty and kernel phi is a subgroup of G and kernel phi is normal in G. So these three, once we establish what is required, we will get. Now by lemma 2.7.5, the first subdivision, this is what we had as lemma 2.7.5. If phi is a homomorphism of G into G bar, then phi of E equals E bar. That is, a homomorphism takes identity element to identity element. So because of that, we have our kernel phi to be non-empty. So definitely my E is a member of kernel phi because phi of E is E bar as phi is a homomorphism. So we have our kernel phi to be non-empty. Then to prove that it's a subgroup, we have to consider two elements, say x and y in K phi. So which means phi of x is E bar and phi of y is E bar. We need to show that xy inverse belongs to K phi. So for that we have to show that phi of xy inverse is identity element, because all those elements which are taken to identity element can only be a member of kernel phi. That is how that is defined, kernel phi. So we consider phi of xy inverse, that is because phi is a homomorphism, we can write it as phi of x into phi of y inverse. But again, because phi is a homomorphism, we have this to be phi of y the whole inverse. The image of any inverse of an element is inverse of the image of the element. So by the second subdivision in this lemma, we have this step. So we have this to be E bar inverse, and of course for identity element inverse is itself. So we have this to be the identity element of the codomain. So this element being taken to the identity element, it has to be a member of kernel phi. So that proves the second one. Next, we have to show that this is normal in G. So because we have to show that it is normal in G, from G I have to consider an element, say G in G, and this has to be shown to be normal in G. So for that we consider an X in kernel phi. Now if we consider Gx G inverse, that should be there. So Gx G inverse should be present in kernel phi. So that is our aim. So for this to be in kernel phi, any element will be in kernel phi provided the image of that is identity element. So for that reason only we start with this. Phi of Gx G inverse, because phi is a homomorphism. We have this to be phi of G, phi of X, phi of G inverse. Again phi is a homomorphism, so we have this step. These two are retained as such. And phi of X is E bar because your X is in kernel phi. So we have this step, and this is an element in G bar with its inverse here. So this has to be E bar. So that in turn tells us that Gx G inverse belongs to kernel phi. So kernel phi is normal in G, that is the domain. Now the next one, we have phi to be a homomorphism of G onto G bar with kernel K. We have to show that the set of all inverse images of G bar in G bar under phi and G is given by this. Where X is any particular inverse image of G bar in G. So we consider phi to be a mapping from G to G bar, which is an onto mapping. And kernel K is all those elements in the domain, which are mapped onto the identity element. That is our kernel phi. So that's taken as capital K. We shall name this as 1. And we'll consider some G bar. E bar is there, that is identity element. Now we shall consider G bar in G bar. We shall denote the set T to be the set of all inverse images of G bar in G bar under phi. So phi inverse of G bar will be all those elements in G for which the image of those elements is G bar. That is how inverse image of an element is described. But by the definition, phi inverse of G bar, inverse image of G bar in capital G bar. If you consider that, the inverse images will be present only in the domain. So phi inverse, the domain means domain of phi, I mean. So for phi inverse, you have phi inverse of G bar. See, as such, we cannot describe phi inverse to be a mapping from G bar to G, for the simple reason that phi inverse will exist only if phi is bijective. So here it is the notation. This doesn't say that phi inverse exists. Phi inverse of a particular element, notation is given by this. So phi inverse of G bar is all those elements in the domain whose image will be G bar. So all those elements which are having the images to be G bar, that collection is only denoted as phi inverse of G bar, and that we shall take as, say, some T. Now let X be any, if X is any particular inverse image, if X is any particular inverse image of G bar, then how we can write that or express it? It is phi of X is equal to G bar. For this G bar, the particular inverse image, that's given in the statement itself. So we have this. This T is named as, this one is named as 2 and this one is named as 3. Now our job is to show that T is Kx. That is what we have to show. The set of all inverse images of G bar in G bar and phi is Kx. So this is what we are trying to prove. T we have mentioned as the inverse image, and Kx is what E has given in the statement, and we need to show that these two are the same. So naturally this is one set, this is another set. To show that two sets are equal, we have to show that one is contained in the other. That is T contained in Kx and Kx is contained in T. Now before that, we claim in the first case that if G bar is E bar, because G bar being a member of capital G bar, it can be even E bar. If that is the case, then what will happen to our T? So it is all those T in G for which phi of T is E bar. That is all those elements which are mapped onto the identity element of the codomain. By the definition of kernel, it is nothing but K. So T is K. So we have, and this we can rewrite as T is equal to Ke, where E is any particular inverse image of E bar, because phi is a homomorphism. We know that it takes identity element to identity element, and so we can interpret this as E is any particular inverse image of E bar. So in this case, we have the result to be 2. T is equal to Ke. Now we shall consider the case where G bar is different from E bar. Then to prove that T is equal to Kx, we have to show that T contained in Kx and Kx is contained in T. So first we shall have this as subclaim 1 and that is 2. So to have the first one, we shall consider one element, say y in T. Our job is to show that this y belongs to Kx. This is what we have to prove. Now let y belong to T. Then phi of y is equal to G bar. That is how the elements of T are defined, those elements whose image is G bar. Because Y belongs to T, the image of Y and phi must be G bar. Now by equation 3, phi of x is G bar, so you replace your G bar by phi of x. And this is group equation in G bar. So we can, in G bar, every element has inverse. So we post multiply by phi of x, the whole inverse, and the right side becomes identity element E bar, and this is what we have on the left side. Now because phi is a homomorphism, phi of x, the whole inverse, can be rewritten as phi of x inverse. Again, phi being a homomorphism, this can be rewritten as phi of yx inverse. So phi of yx inverse is E bar. And all those elements which are mapped onto identity element by the definition of kernel is nothing but a member of this kernel. So yx inverse should be in K by the definition of K. So let us take this yx inverse to be some small k, where k belongs to capital K. Small k belongs to capital K. So this can be rewritten as y is equal to kx, where is our small k? In capital K. So I can very well rewrite this as y belongs to kx. So y in t implies y in kx, therefore you have t contained in kx. So that proves the first part. Now for the second one, we shall consider now y to be a member of, you can even take this as some z also. So let y belong to kx, then y is equal to kx, where small k belongs to capital K. Now phi being a mapping, when the elements are equal, the images must be equal. So we have this step, phi of y is equal to phi of kx, and this is phi of y into phi of k into phi of x. This is by we have this one should come here by G bar, by 3. So phi of y is equal to phi of k into phi of x, but k being a member of capital K kernel, in kernel we have all those elements taken to identity element, so this becomes E bar, and by 3 you have phi of x to be G bar. So E bar into G bar is G bar. So phi of y is equal to G bar by 2. So we have this is not by 2, it is G bar, E bar into G bar is G bar. So we have this, and whenever we have phi of y is equal to G bar, where should our y be? Those elements whose image is G bar should be present in T. So my y is of that kind, therefore my y should be in T. So we started with y in kx, we have got y in T, therefore kx must be contained in T. So that proves the second subdivision of this subclaim. So we have T to be equal to kx, T contained in kx, kx contained in T contained in kx, kx contained in T. Clubbing these two, we have T to be kx. So now we have this result which states that if G and G bar are any two groups in the collection of all groups tau, then being isomorphic is an equivalence relation on tau. We consider tau to be the collection of all groups. You may have different groups with different operations. We are not bothered. So we have tau to be collection of all groups. Now what do you mean by being isomorphic? That is, whenever we say that G is isomorphic to G bar, means we can always have an isomorphism of say phi from G onto G bar, G onto G star. Here we consider G and G star to be any two groups over here. So this is how the relation is defined on tau. So we need to have a set and then a relation. So this relation is defined as, for any two elements in tau, namely G and G star, G is related to G bar, G star, if and only if G is isomorphic to G star. So this is how we are defining this relation on tau. Tilde on tau is defined in this way. So we have to show that this relation is an equivalence relation, which means we have to show that it is reflexive, symmetric, and transitive. So first we will prove reflexivity, that is any group is isomorphic to itself, that is G is isomorphic to G. And the second, if one group is isomorphic to another, then the reverse case is also true. That is, if G is isomorphic to G star, then G star is isomorphic to G. And transitivity, if one group is isomorphic to second and the second is isomorphic to the third, then the first is isomorphic to the third. So that is, if G is isomorphic to G star and G star is isomorphic to G double star, then G is isomorphic to G double star. So first we'll prove the reflexivity. So between that G and itself, which one will act as one-to-one onto homomorphism? Obviously, it is the identity mapping. So if we consider the identity mapping from G to itself, which takes any element to itself, so in that case we have this mapping to be one-to-one onto homomorphism. In the examples we have given, identity mapping is always a homomorphism. So we have that mapping serving the purpose to show that G isomorphic to G. Now for the second one, we shall assume that G is isomorphic to G star, which means phi from there exists one onto isomorphism, say phi from G to G star. Now here isomorphism we have considered one-to-one homomorphism according to Huston. It is one-to-one homomorphism. So if already here you have onto, so onto one-to-one means you have bijective. So phi is bijective. Because phi is bijective, its inverse will exist as a mapping from G star to G, and that is also bijective. So this is a result that is known to us already. Inverse exists only if the given mapping is bijective, and that is also bijective. So that result is borrowed here. And now we'll show that phi inverse is also a homomorphism. That is, it preserves the group operation. So we will consider two elements in the domain G star, namely G1 star and G2 star, small g1 star, small g2 star. Now we will consider phi inverse of G1 star to be G1. It should have image over here. So we shall take that as G1, and image of G2 star under phi inverse is taken as G2. So these two we are considering. Now, because phi is a homomorphism, having got G1 and G2 in G, phi is a mapping from G to G star, which is homomorphism. So, and G1, G2 being members of G, we have that phi of G1, G2 is equal to phi of G1 into phi of G2. Now, if we consider this phi of G1, we have that phi of G1 from here. See, phi of G1 is nothing but G1 star. And similarly, phi of G2 is G2 star. So, okay, first we shall consider this one. So, that is, we have phi of G1 into phi of G2, giving us G1 star, G2 star. And that is phi of this G1 is nothing but phi inverse of G1 star, and this G2 is nothing but phi inverse of G2 star. From here we are rewriting this. So first this is considered, that is G1 star, this is G2 star, and this one is this. Now if I apply phi inverse on both sides, then we have this. So, but phi inverse being bijective, phi is bijective, so you have the inverse and the original, so that gives identity mapping. So phi inverse of G1 star, G2 star is phi inverse of G1 star, phi inverse of G2 star. So what is to be remembered here, that is, see, we used to say, GPTC, you have what is given, what is to be proved, the technique involved, and the conclusion. So for this part, see, for the entire proof, you can use this GPTC rule. Even a part of it, when you prove something, for that also you can use this rule. So here you are given phi to be bijective and homomorphism. So because it is bijective, phi inverse exists. So what is given from that, these are the inference. Now here phi inverse bijective is known result. So what is unknown is only phi inverse is a homomorphism, that is to be established. So for that we need to consider two elements in the domain. But the way in which our phi inverse is defined, we can have for this G1 star on image over there, that is taken as G1 in G, and this one is taken as G2. So here we make use of the fact that phi is a homomorphism. We make use of the fact that phi is a homomorphism. So this is the technique, main technique. We make use of the fact that phi is a homomorphism. And then this is rewritten from here, because once you have this, you have G1 star to be equal to phi of G1. So that is the reason why you are replacing your phi of G1 by G1 star here. And similarly here. So these are known to us, and this is the technique actually, because you know that phi is a homomorphism. So from that only, and then you have this technique, that is you need to apply phi inverse on both sides. So that is another point to be noted. So these two are the key points to have the proof of this part. So phi inverse is a homomorphism. Phi inverse from this is bijective and a homomorphism. So you have G star isomorphic to G. Now for transitivity, we shall assume that G isomorphic to G star and G star isomorphic to G double star, and that should imply G isomorphic to G double star. So we shall consider two mappings. Because this is true, we have to have this G isomorphic to G star. We should have had our phi from G to G star to be 1-to-1 onto homomorphism. And for this part, we'll consider another mapping from G star to G double star, which is also 1-to-1 onto homomorphism. Now we know that whenever phi and psi are bijective, their composition is also bijective. So here when you are writing the element to the right of the mapping, psi composition phi is to be used. So we need to show that the composition psi composition phi from G to G double star, G to G star, and then G star to G double star. So phi comes here, we operate, So psi composition phi, we have to show that bijective homomorphism. But because composition of bijective mapping is bijective, we are not establishing this. Our aim is only to prove the homomorphism part, that is, this one preserves group operation. So for that, we'll have to consider two elements in the domain. We shall take them as G1, G2 in G. So psi composition phi of G1, G2. By the definition of composition of mapping, it is phi of G1, G2. And phi being a homomorphism, that's given to us. Phi is a homomorphism. This is a homomorphism. So we have to have phi of G1, G2 to be phi of G1, phi of G2. And then this again. So this is one element. Where is it? This is in G star. See, phi of G1 will be in G star. So for psi, G star is the domain. So it will we can rewrite this as psi of phi of G1, psi of phi of G2. And by the definition of, so this is because psi is a homomorphism. This is because psi is a homomorphism. The first one is because phi is a homomorphism. And this is because your psi is a homomorphism. So we have made use of what is given to us. So from this we have psi composition phi to be a homomorphism. So again, for this part, if you consider GBTC, now what is known to us is this. So this is what is given. And what is to be proved is psi composition phi is onto isomorphism. And the technique involved is we have the phi and psi. This is the known assumption that is used here. So nothing special that we have considered. So we have psi composition phi bijective homomorphism. Therefore, from G to G double star. So G is isomorphic to G double star. So being isomorphic is an equivalence relation on the collection of all groups. Thank you.